Hi everyone, my name is Vladimir Tsymbal. I'm a technical consulting engineer at Intel Architecture and Graphic Solutions Group, and today I'll spend this hour giving a quick overview of the tools which are helping to analyze performance of your DPC++ applications on Intel GPUs. And yeah, just to briefly in this presentation, I will quickly introduce to the GPU programming model that is supported by our tools, and then I will give an overview of analysis types for GPU and VTune, or VTune profiler, which is the full name. And there are two types of analysis, which are offload offload analysis and GPU hotspots. Will be demonstrated on some simple code sample. And then I'll also give a quick introduction into Intel Advisor tool, which is already mentioned by Professor Illich, but in the recent, in the previous presentation, but in terms of analysis of executing the applications on GPU, which is offload analysis for GPU and GPU Roofline. So I'm actually not going to go too much to the programming model, just to mention that all the Intel GPUs, the generations like 9, 11, 12, available right now on the market, they are supporting different approaches for programming, including based on SDKs like Media SDK, based on C API, direct programming with OpenCL, SQL, or data parallel C++, and of course libraries which are going along with OneAPI toolkits. All these models are supported by performance analysis tools that we are going to talk about today. So just to give a quick overview of analysis tools. So we are supporting the analysis of compute media hotspots. Compute means GPU execution, and media is for media applications running on GPU. With using the specific hardware counters, which are embedded into GPUs, and with help of runtime analysis counters, which are part of the software stack. Also, the tools, the analysis tool is providing the in-kernel profiling for low-level source or instruction-level profiling based on software instrumentation. So the main idea actually is to understand which kernels which are executing on GPU needs to be analyzed and profiled, and quickly find out the best candidates to improve the performance after the analysis of application. So VTune is quite known tool for analysis applications on CPUs, but now with GPU, we have the aggregated views for data based on either kernel or function calls or different other angles of view of collected data. The timeline views, which are representing the overall picture during the execution, what's going on with GPU and CPU, and architectural diagrams of Intel GPUs, and some metrics which are applied on the blocks of this diagram. We'll talk about that a bit later in more details. So GPU analysis is provided along with in-kernel profiling. So either with DPC++ or OpenCL code, you can get the performance information against the source lines or assembly instructions. In the same time, the I would say from the CPU side, the DMA packets being sent for execution, the jobs being sent to for execution in the queue for GPU can be analyzed as well, and VTune is providing the different views on this execution, in, like histograms or queue depths and things like that, and all these execution comments they go along with their call stacks collected while analysis. So let's start with offload performance tuning. So if you open the configuration window of VTune, you'll find out specific types of analysis, which is analysis for accelerators, and one of those is GPU offload. You might notice that it's a preview type of analysis. It means that it's really actively developed, and the interface or the views can be changed with the time because it's still under development, and it's very dynamically being developed in the moment. So this offload, GPU offload analysis is supporting all heterogeneous applications that are available at Intel toolkits, including OpenCL, SQL, DPC++, and OpenMP offload. And the specifics, what's specific about this GPU offload analysis, it's looking not only at GPU, but at the CPU as well. So you will get the entire picture, how CPU and GPU are interacting, how the jobs are being submitted and waiting in the queues, and what are the threads, how the threads are busy with submitting these jobs on CPU side, and how the GPU is doing in the same time. So the main goal in this analysis is to identify the efficiency of actually on both sides, on CPU and GPU, and to find out if a workload is GPU bound or CPU bound or both, and which kernel is better to focus on in the future to increase, in order to try to increase the performance running on GPU. For CPU efficiency, of course, there are other analysis types to consider. So we will consider the simple DPC++ sample application. Yeah, in the earlier sessions, it was already explained what DPC++ is. I don't need to repeat that again. So we have a bunch of sample applications available on the GitHub. I think there was a link later in the next slides. So I just took the simplest one, and the matrix multiply will like it, and we show that all the time. It's extremely ineffective implementation of matrix multiplication on DPC++. That's for purpose, and it helps actually to see how the tools can help with finding out the places where the code is inefficient, and hopefully is helping developers to improve the performance of DPC++ applications or SQL applications or OpenCL applications. Actually, it's not fully offload example because, well, since this concept of single source for DPC++ is when you are using both resources, CPU and GPU, that would be the most desirable case, but in our case, this is only GPU bound application. So that's just a small part of this sample. Here's the link on the GitHub where you can download it and check. So multiply one, I would say it's kind of naive implementation of matrix multiplication with DPC++. Yeah, we don't want to go too deep into you know, understanding what each source line is doing. So basically, it's combination of submitting of queue and you know, assigning the accessors to buffers, and actually the parallel construction, which is parallel 4, and the kernel itself is implemented as a lambda function for executing the matrix multiplication. So let me switch to the tool and continue to show in this example. Okay, I hope you can see the interface of VTune. So I'm using the latest One API basic toolkit beta 9 VTune, which is it's part of this toolkit, and I pre-collected some results on my machine on the laptop that I'm doing the presentation on. And so let me start with offload analysis results. So VTune is giving, in the summary, is giving some basic characteristics like overall timing for execution of application, extremely important metric, which is GPU utilization, is how much in terms of runtime of application the GPU was busy with doing something. And there are some recommendations that, you know, for this particular workloads, GPU utilization is quite low, and probably you need to understand to find out why there's a poor GPU utilization for this app. And some additional insights on execution units array inside GPU, which are stalled like almost 40% of time when it was busy. It was busy, but it was stalled with waiting some data from memory. And yeah, you will get the hottest computing task. In our case, it's just single task, multiply kernel. In the real life applications, it would be many kernels, and VTune would sort them by the time it took to execute the kernels. Since it's a iGPU, it's a embedded GPU machine inside in the CPU. So you might want to understand how the access to memory in terms of bandwidth, how busy it was fetching data from main memory, and you can analyze it using the histogram of memory access. But the main data can be found in the graphics tab. Let me switch to it, and again, we have only one kernel which is being executed in this application, and VTune will provide this aggregated view for this kernel. And actually, this kernel was called just once, and that's why this instance count is 1, and it's providing the time for this kernel execution. Some characteristics regarding the size of the task and the efficiency of arrays or execution unit arrays in during runtime of this application. So as we can see, like 38% of time they were stalled waiting for some data from some level of memory. It could be global memory or whatever. We don't know from this analysis yet. Well, also, although we might notice that the threads occupancy is quite high, 95%, which indicates that there was enough job for the number of threads available for execution. So if this number is quite low, it would be highlighted with the pink color, and it would indicate that we probably didn't provide enough job for executing in many execution units or in many threads of this GPU machine. At the same time, we can observe the timeline a picture of a combination of activity of CPU on the system and GPU tasks being submitted for the on this machine. So it's a single task, which is quite interesting. How much this CL link program, how much it takes actually to prepare this kernel to execute on GPU, and then we can observe that with this CL wait for events is actually waiting on when the kernel is finished, execution on the GPU side. In the same time, there are some timeline characteristics of GPU here. Is the arrays being active in each time slice, and some other characteristics like how many computing threads started per second, GPU utilization, and frequency of GPU. That's actually it, and unfortunately, this example is not the best to demonstrate this analysis type, because the main idea actually to identify which kernel is better to analyze among many of kernels, and which one is maybe taking a lot of time, but the efficiency is quite low. In this case, we're just observing one kernel, but it still can give quite, can give enough information on to understand how efficient the execution of this kernel was in the application. So let me switch back to presentation. Well, I hope everybody could see this VTune example. Yes. Because I don't know if it was sharing nicely on the screen. Okay, thank you. So let's get to the next one, to the second type of analysis for GPU is GPU hotspots or compute media hotspots. That's kind of maybe not final name of the analysis, because this type of analysis can provide the information of the hottest execution points either for GPU workloads or for media workloads. So in this case, we are using this type of analysis available in the VTune configuration, and now it's a purely GPU analysis. Although there are some other metrics in the system on chip can be measured, is like bandwidth metrics, latency metrics, and so on, which is related overall to the system or to the SoC, to the system on chip. So, the idea is how to get the maximum performance out of the GPU. Ideally, in the ideal world, we would be using. We would be happy to using some performance libraries like MKL, which would do all the job for us, right? And we would not bother with this optimization for specific GPUs. And yeah, in most cases, this is the recommended way. However, with these high-level languages like SQL or DPC++ or OpenCL, we still have some room for improvement or tweaking our source code, and sometimes we need to do that, or sometimes we are the developers of the libraries, and we need to analyze these kernels. And in order to do that efficiently, you need a little bit to know the microarchitecture of GPU. It's the same applies to CPU as well, as you know. So that's why we need to understand at least the basics of GPU we're working with. So at the moment, I'm working with this laptop of the previous generation, which is equipped with this UHD graphics 620, which is Gen 9, and with 24 execution units, with maximum workgroup size 256 and 64 kilobytes of local memory. So let's maybe take a closer look in the execution unit itself. So we need to know that each execution unit can run up to 7 threads. So it can be up to 168 threads simultaneously, even on this small GPU in my laptop. So it makes it means that you need to think about enough job to do for the GPUs, because even in this small GPU card there is still huge amount of threads available for doing something. So it has a 128 general registers in the file of 32 byte, and they're quite flexible and can fit vectors of different sizes. Each execution unit can it has 2 CMD devices, or FPUs, floating point units, even though it's FPU, and in the same time it can execute the integer operations as well. So it can make up to 16 multiply add operations per cycle, and then multiply per 2 FPUs and their CMD width. And there are 2 additional execution units which are branch and send. So the main idea here is to, if you want to increase the efficiency of execution of the workload, you need to maximize utilization of this machine on these execution units. That's that would be 100% true if your algorithm is kind of optimal one, which means that you still can make the GPU busy 100% of time. It doesn't necessarily mean in real life that it's the best implementation. You are using the best implementation of your algorithm, and with the simple examples of matrix multiplication, it's quite easy to demonstrate. So well-known inefficient implementations of this matrix multiplication example, they can make completely busy and hot any GPU, but it still can be inefficient. And unfortunately, the tools are not, the tool like VTune cannot help in, in understanding whether this algorithm is efficient or not. It's up to us to get the numbers from analysis and see how much data is being transferred here and there and so on. And we will see that in an example, how we can find it out. So actually in this CPU compute media hotspot analysis, there are different flavors or different options for analysis. And there are 2 main or basic ones. It's characterization and source analysis. For understanding the GPU engine usage, you use characterization, and it will give you the efficiency of execution, the stalls while executing the tasks, the kernels, and so on. The source analysis is helping you to identify the blocks which would be in the source code, which would be performance critical for execution, and the problems with memory access. So here's the then the optimization strategy behind the tools analysis. You are trying to maximize the execution unit utilization. You need to maximize the CMD usage per each execution unit, and you need to minimize the stalls due to memory accesses or inefficient memory accesses for execution units. Inefficient means it has some certain latency which is increasing with if the data is being fetched from a distant memory. For example, the global memory is the most distant one for that microarchitecture. So with selecting the characterization flavor of this analysis, you will get these execution units activities, like how many EUs were active, stalled, or idling, how many competing threads started, and the frequency of the GPU core. And in this characterization, there are also sub-flavors, I would say, overview or compute basic metrics, which are providing some additional metrics with how bandwidth of read-write bandwidth to memory, level 3 cache misses inside GPU, and memory read-write transactions of different types. In the another flavor of characterization is dynamic instruction count, or you can call it preset. So actually, it's collecting the information about the instructions being executed in your kernel, and yeah, it groups that by type of instructions, which are control flow, send, synchronization, executing like int, float, and different sizes of these operations, and some other. And in the end, you will get this distribution of this type of instruction against each kernel of your application. So the next analysis set or predefined set is source analysis. Is when you can observe the instruction execution against source code of your DPC++ or SQL or OpenCL application and assembly. And actually, this is quite powerful method of understanding how actually the compiler implemented your algorithm, and why, for example, the CMD was not used at all, or the width is not fitting the capability of the machine, and so on. So let me switch back to VTune to demonstrate the this type of analysis. Okay, so let me maybe close this result. And I pre-collected another one, a little bit more improved version of matrix multiplication, still not efficient, but it runs a little bit better. So in the summary for GPU hotspots, we are getting this information overall on amount of execution units, the percentage of execution units, the percentage of time while it was stalled, means waiting something, most probably data from memory units. There are some other metrics like occupancy of the execution units array, which is also indicator of efficient distribution of works between the units. Now we get the FPU utilization, which is indicating of the amount of time when EU was busy, how much time, what was the portion of utilizing the executing unit itself, the floating point unit itself. So the goal is to make it as busy as possible. Otherwise, you need to balance somehow the code, the execution code and data handling code to make it like more effective or more balanced. By the way, in the summary, if you open this collection platform info, you can observe the name and some characteristics of your GPU which you are running on. This is EU count, the maximum threads per EU, and so on. So this is the dynamic information collected by VTune. So let us switch to this single matrix multiply kernel in the graphics tab. So we will get this aggregated view per compute task with some characteristics and a graphics diagram against this kernel. So now it's a little bit more improved version of kernel, which is running like 5 times faster than the previous version. And well, probably this implementation was done with using the tiling of matrices, which is well-known approach, or well-known method of increasing the cache efficiency. Now it's still the kernel was called just once, and now we can observe that CMD width is 16. So we are kind of efficiently using the CMD operations in the execution units. So the arrays are still not 100% active all the time, so they are stalled for 42%, and it's another reason to take a closer look of efficiency of this kernel. Although at the same time the threads occupancy is fine enough, it's 85%. Well, there's some threshold which is making this pink, because well we are expecting the occupancy higher than 90% to call it efficient. And what you get in addition is the EU instructions. So it's only 22% of time both FPUs were executing actually real instructions, and yeah, the rest it was either idling or used for like send operations. And you might notice that there is an IPS instruction per cycle rates calculated, which is quite not that low, but still far from ideal, which would be 2. Yeah, there are some additional metrics regarding the data. It's indicating that it's very close to the limits for bandwidth with level 3 cache in the GPU. And maybe it's a good time to take a look at the diagram of this GPU, because this is exactly the high-level representation of this GPU that I'm working with, and it gives these numbers regarding the bandwidths and amount of data being transferred from different levels. So in order to switch between the bandwidth numbers and total size, we can use this context menu, and then we can observe how much data is being fetched from last level cache of the CPU, actually from DRAM and through the GTI interface, and how much data is being exchanged with level 3 cache inside GPU itself. So you might notice that totally like 77 gigabytes of data is being transferred here and there, which kind of indication of inefficiency with handling the data for such a size of the matrix, which is 2048 by 2048. So it's a good indication of reconsidering the algorithm and try to understand maybe there is a better way of implementing the access to memory units. Although we decreased significantly the amount of data being fetched from DRAM, but and most of the data is in level 3, but still, which is much faster. That's why the kernel is running faster way. But still, because of huge amount of data is being transferred here and there between execution units and level 3 cache and GPU, that might be a source of another, another source of inefficiency. So this diagram is really helping to understand what's going on with data inside the kernel, and this data is displayed against each kernel. We have a single one, but if you select another one, if there was another one in the application, so it will change to reflect this particular kernel.
Real quick, there's a question on the side about this current topic.
Sure.
How do you know in VTune which parts of the code are responsible for most of the data movement of CPU to GPU or GPU to CPU?
Okay, that's a great question. Unfortunately, in this presenting mode, I don't see these questions, but okay, VTune is, to give a little bit more details, VTune is using different sources of information about the kernel. So in the graphics driver, there is an MD API interface, which is providing the runtime information about the kernels and the data related to memory access and caches and so on. This is low-level data based on hardware counters. In addition, VTune is taking information from runtime, which is either OpenCL runtime or level 0 runtime, which is new runtime in Intel toolkits, Intel compiler. It's the information mostly regarding the tasks and jobs being set placed into the queue for execution. And in addition to that, VTune is using the GTP is an instrumentation engine, which is instrumenting the code on fly dynamically, which will provide the information about the source code. So, and this one is because it's instrumentation-based analysis for source code. We'll talk about that in a few seconds. So it creates some noticeable overhead, and you will see that this overhead while analysis. So many sources of different types of different metrics are used inside VTune. I hope I answered the question.
I think the question was just slightly different. They want to know how you can see which parts of the code that are responsible for most of the data movement.
Oh, this is what okay, sorry, maybe I misunderstood that. I was going to come to that in a few slides.
Okay, thank you.
Okay, so let me switch back maybe to presentation. Oh, it's I'm wrong. I was going to go back to VTune. Sorry for that. Yes. Okay, so let me switch to the source analysis results. When I selected this flavor of analysis or preset, so if I go to the graphics tab, so there is not that much that I can observe in this aggregated view, because it's just estimation of GPU cycles per each kernel. It's intended to give a bigger picture for many kernels being executed in a real-life application, and it gives some this distribution of cycles, and is providing the latency for different operations like memory access and synchronization. But if we go to the function itself in this computing task, so I double click on this function name, and then I get this latency cycles and estimated GPU cycles, the portion against the source code inside my kernel. I hope this this is the answer on this question. Okay. Yeah, and if we press this assembly button, we can observe this corresponding assembly lines which are implementing this source line. So they are dynamically highlighting each of the line, and then so we can have a quick info on implementation of this matrix multiplication by the compiler, and which instructions are used for adding and multiplication in my algorithm. Okay, so maybe I should probably have shown the configuration window for the VTune and the selection of different analysis types. On the right side here, those are the accelerators, the analysis for accelerators, because we have another additional type for CPU and FPGA interaction, which is also considered as an accelerator and which supports DPC++ as well, but it's not a topic of our presentation today. So we are selecting one of those, either GPU offload or compute media hotspots. And the rest are related to either platform or CPU analysis. Okay, let me switch back to the presentation. So the next topic in the presentation was the advisor. So Professor Illich described this cache-aware roofline model, which was implemented in advisor for a long time, and he was actually contributing to that work. And just to give a quick overview on advisor, it's actually more than just roofline analysis. It started as the tool which was modeling the performance of application in terms of vectorization or threading, and now it's added some modeling of heterogeneous algorithms, and offload, advisor, and roofline analysis. They are now related to GPU as well. So we will quickly review those two analyses because they are related to GPU. So yeah, in the general workload, whichever code you have to analyze, it could be existing C++ or Fortran or C code or OpenCL application, or some code which is converted from CUDA project. So you can apply advisor and to create some models and to find out which places in the code are the best candidates for offloading to accelerator. That's the main task for offload advisor. And once you identified those and you created those kernels, you can use the roofline model for analyzing those and to understand the main limits in the current architecture, or make a projections for other architectures. maybe not necessarily available at the moment, and to find out what are the limits and how to improve the kernels for that architecture. So that's why we have two types of analysis in Advisor, the offload and GPU offline. Let's start with the offload Advisor. So just quickly to give you a main idea. So it's a new GUI interface, graphical user interface that available only from one API toolkit beta 10, which is about to be released. It's also available in beta 9, the current beta 9, but with some certain environment variable can be found in documentation. So you open the perspective selector and then select the offload modeling tab, and then you need to press the choose button to set which actually architecture you want to make the performance projection. It's either the existing on the market like Gen 9 or Gen 11, or there are some hidden architectures which are not available publicly, but internally the tool is used for projection for other future microarchitectures. So you just select the target device model, you select the accuracy because you need to control the overhead, and you run the analysis of existing code and make this performance projection. Of course, not every GPU is installed on a nice desktop with a graphical user interface. Many people are running their workloads on remote machines like remote clusters or some other facilities. So that's why the full-fledged command line interface is available. So to do that, to run the offload advisor, you just need to run a script with the specific performance model and providing these parameters, and then you generate the offload report, which is available in HTML file, or you can open it inside the tool. That's quite easy. So before this beta 10, we had the HTML report only. Now we have this ability to see that inside the tool. So it will be some the top metrics for the whole application. So what is the overall speed up projected to specific GPU architecture, which fraction of the application is going to be accelerated, and amount of offload regions which are proposed to be accelerated. Then it will give you the comparison of accelerated versus non-accelerated timings in the application, and some characterization metric for the whole application in terms of measurement of caches on main memory and things like that. Yeah, just for increasing the usability, you can focus on the top 5 regions which are compared if they are offloaded or not offloaded. So it's a very quick and nice tool to find out, to explore your application in order to decide, okay, here's the region I probably want to accelerate because the tool says me I'll get that amount of projected performance improvement. Yeah, it's of course it has a limited application because if you are developing the accelerated code, you already know from the beginning, from the design, that this part is going to be accelerated. But on the other hand, there are a lot of applications which are under consideration to improve with GPU accelerators, and you would need this tool to understand how much you can get out of this acceleration on GPU. So then let's switch to the GPU Roofline. So it's already been discussed before. The Roofline analysis is a kind of powerful and very very useful tool, which in a graphical way represents the limitations of the absolute limitations of the system in terms of memory units benefits and the execution units performance, and where your algorithm and specifically loops or function calls are located in this graph. If it's going to be limited by access to memory hierarchy or by execution units, and you might want to either improve your data access pattern or change your implementation of your execution, like using vectorization and so on. So in the GPU Roofline, we have the memory units added, which is like GTI interface or shared local memory. So it's actually very similar to Roofline model for CPU, but in this case we are having additional lines on the memory slopes and some similar horizontal lines which are indicating the limits of execution units. So again, with using this graphical user interface, you open the perspective selector and select the GPU Roofline, and then you need to press the choose button, and that would work from a graphical user interface. With the command line, it will take a little bit more effort because you need to collect two types of analysis: is the survey with this profile GPU option, and the trip counts for the loops for the profile with the profile GPU option. So overall, those two analyses will create a GPU Roofline report, and this Roofline report can be in command line, that it can be viewed in the Roofline HTML in the graphical representation of based on HTML file. So the same similarly, you can do that not only for floating point but for integer operations as well. And then you can visualize the results using the web browser. So very similar approach which is used like in CARM with addition to some levels of memory like GTI or shared local memory, and the same level 3 GPU caches, and they are the rest. The approach is still the same for analysis of this Roofline and for understanding where are the limits of your algorithms or the implementation of algorithms as a function calls or loops, which are displayed as points on this Roofline graph. So if you are familiar with Roofline analysis on CPU, the GPU Roofline is very similar. So that's actually concludes the presentation. There are some useful links when you can explore the new types of analysis, and take a look at the cookbooks available for both VTune and Advisor. There are nice examples and step-by-step explanation how to use the tools, how to interpret the results, and some other useful links available. So we have like 5 minutes for questions. I would be happy to answer them.
I don't see anything popping up on the QA right now. So
okay, I'll switch to Slack then and follow up if there are some questions.